everyone, welcome back to another session of our CISSP study group. I'm B-Dubs, and I'm excited to dive into these topics with you today. Whether you're working hard to pass the CISSP exam or you're just a nerd about cybersecurity, you're in exactly the right place. I truly appreciate your dedication, and I'm stoked to be on this journey with you. In our last session, we finally completed Domain 7, covering objectives 7.14 and 7.15. If you missed it, don't worry. I've made a playlist to help you catch up at your own pace. I'll drop the link in chat now. Today, we're in that home stretch, starting with our final domain, Domain 8, Software Development Security. So let's get right to it. Today, we're focusing on objectives 8.1, Understand and integrate security in the software development lifecycle, and 8.2, Identify and apply security controls in software development ecosystems. These are important because software is everywhere. It's in your phone, car, and even your air fryer now. If it's not secure, we're all vulnerable. First, we'll look at how we can integrate security into the software development lifecycle, or SDLC. Then we'll learn how to secure the software development ecosystem with proper controls. Think of it as a two-part mission: secure the process, then secure the tools and environment. Rush security is like waiting to patch critical vulnerabilities until right before launching our application. That chaos shows us that security can't be an afterthought. So let's learn how to get it right from the start. So what is this SDLC? The Software Development Lifecycle, or SDLC, is a systematic approach to building secure and reliable software. Think of it as a recipe for software development. It's a structured framework that guides you from planning through coding, testing, deployment, and maintenance. Without it, you're just throwing code together and hoping it works, which it rarely does. The SDLC keeps everything on track, but here's the key. Security has to be baked in at every single step. You can't just sprinkle it on at the end like your salt and pepper. Let me paint you a picture of how the SDLC works. It's just like building a secure house. First, we've got our foundation. This is the requirements phase. This is where we ask ourselves, what security measures do we need? What are we protecting? And who are we protecting it from? Next comes the framework, which is our design phase. Just as you'd plan where to place security cameras and alarms in a house, we're mapping out how our security controls will all work together. Then we move to construction, or our development phase. This is where we're actually building those security measures, like installing reinforced doors and windows. Every line of code must be as strong as a steel door. Finally, we've got our testing phase. Think of it as our final security check. We're not just testing each component individually. We're making sure all our security systems work together seamlessly. After all, what good is a fancy alarm system if it doesn't communicate with your security cameras? Now, which SDLC phase do you think is the make or break for security? So let's break down these SDLC phases and see how security integrates throughout each one. Remember, security isn't something we just bolt on at the end. It's integral to every step of the process. First up is requirements gathering. This is our foundation. Imagine you're building a healthcare app with HIPAA requirements. You'll need three key things: a security requirements traceability matrix to track everything, compliance checklists, and detailed security controls inventory. Moving on to design, this is where we create our security blueprint. We use powerful frameworks like Stride and Dread. Stride helps us think like an attacker by looking at things like spoofing, tampering, and information disclosure. Then Dread helps us prioritize those risks by evaluating potential damage and exploitability. Then we move into development. This is the coding phase. This is where we put our OWASP top 10 knowledge to work. We're preventing injection flaws like those nasty SQL injections, implementing rock-solid authentication, and making absolutely sure that our sensitive data stays secure. Testing is next, and it's so important. We run unit tests on our security controls, make sure everything works together with integration testing, and conduct thorough penetration testing, both black box and white box approaches. We also validate that we meet all of our compliance requirements. Finally, operations and maintenance. But don't think we're done with security. This is where the rubber meets the road. We maintain 24/7 monitoring because threats don't sleep. We keep our incident response procedures ready, perform quarterly security assessments, and follow a solid patch management schedule to keep everything up to date. Security isn't a one-time task. It's continuous throughout the entire SDLC. Each phase builds on the previous one, creating layers of protection. Remember that by catching issues early, like during threat modeling in our design phase, it prevents costly fixes later. Now, the SLC is the complete story of a system, not just building software like the SDLC. Think of it like building and maintaining a house. While the SDLC is like the construction phase, the SLC, or system lifecycle, covers everything from choosing the location to eventual demolition. The SLC is a comprehensive framework that manages an information system's entire lifespan, from initial planning all the way through retirement. Let's walk through this using an example in healthcare, building a patient management system. The initiation phase lays our groundwork. We focus on three main things: documenting risk assessments, ensuring compliance with requirements like GDPR and HIPAA, and allocating the right security budget. Here we ask, what security requirements do we need to meet? HIPAA compliance is critical since we're handling sensitive patient data. We conduct a thorough risk assessment and secure buy-in from all stakeholders, which includes our doctors, administrators, IT staff, and everyone who's involved. Next comes the development and acquisition phase. This is where the SDLC magic happens. Whether we're building from scratch or selecting a vendor solution, we implement robust security controls like encryption, access controls, audit logging. This means creating a security requirements traceability matrix, conducting thorough vendor assessments, and implementing robust testing protocols. It's like building security checkpoints at every stage. Implementation is important because we can't just flip a switch and go live. We need proper certification and accreditation. Think of it like a safety inspection for your car, but far more intensive. We run comprehensive security testing to make sure everything is locked down tight, and we review all documentation. You can never be too thorough here. During operation and maintenance, we're in full protection mode. We maintain continuous monitoring for threats 24/7 because attackers don't sleep, with incident response procedures ready to go, and we stay current with security patches and updates. In healthcare, outdated software just isn't an option. Finally, there's disposal. Don't underestimate the importance here. When retiring the system, we must sanitize data properly, wiping patient records securely, and the hardware needs decommissioning following strict security protocols. And don't forget about proper archive management here either. Remember that security must be woven throughout each phase, from initial planning to the final disposal. All right, your software is live. Sweet. Now the real work begins. Operation and maintenance is where security becomes critical. This works like running a high security facility with three important monitoring tools. First, we have our SAMM systems. These are the central nervous system of your security operations. They work 24/7, collecting and analyzing data from every corner of your network. Without these, you're flying blind. Next are IDS and IPS systems. These are your frontline defenders. They constantly scan network traffic for suspicious activity. When they detect threats, they either raise alerts or, with IPS, they automatically block them. Finally, there's log analysis tools. These are crucial for providing a complete picture of your system. Every login, file access, and configuration change is recorded and analyzed. This digital paper trail becomes invaluable during incident investigations. Now, your patch management timing is vital for your system security. The prioritization schedule might go something like this. Your critical issues, which includes active exploits and severe vulnerabilities, they need action within 24 hours, no exceptions. High priority security holes get 1-week windows. But don't wait until the last day. I see you procrastinators. Medium priority updates might have a month's window, although earlier is better. Minor improvements and non-security updates fit into your regular maintenance cycle, but don't forget to keep tracking them. Don't let them slip through the cracks. Security checkups are non-negotiable. These are regular health checkups for your system. Monthly penetration testing is important because threats continue to evolve rapidly. Quarterly code reviews let your team hunt for security weaknesses that might have slipped through development. Automated security scans must run 24/7. These are your guards that are constantly watching out for vulnerabilities. And yearly comprehensive security audits provide detailed examinations of your entire security posture. You also need solid documentation for 4 critical areas. With emergency patches, you need clear processes for urgent vulnerabilities, including who to contact, how to deploy, and verify. For your routine updates, you need documented procedures to make sure you keep up that systematic maintenance. Then, we have incident response. When problems come up, you need the exact steps to follow. And finally, your ongoing security monitoring. You've got to detail what to monitor, how to monitor it, and then response procedures for any suspicious activity. Remember Equifax back in 2017? Delaying a known vulnerability patch for 2 months led to 147 million stolen records. Don't let that be you. In maintenance, speed and process are your best friends. Moving into change management, this is your systematic approach to modifying live software safely and securely. Think of it like a well-orchestrated construction project. You need proper planning, approvals, and safety measures. The change management process follows several important steps. First, we have the request for change, or RFC, where you document what needs to be changed and why. This could be anything from new feature requests to critical security patches. Next is the impact assessment, where we analyze thoroughly. We examine security risks, system dependencies, and potential effects on business operations. Never skip this step. It's your early warning system. Then we have our Change Advisory Board, or CAB review. These gatekeepers review changes based on type. Standard changes are the pre-approved routine updates. Normal changes might be regular feature updates requiring full review. And then emergency changes are critical fixes needing expedited approval, like zero-day vulnerabilities. After approval, implementation planning begins. Here, you create both a detailed rollout plan and, equally important, a rollback plan in case things go wrong. Before production deployment comes testing, where we validate everything in non-production environments. Remember to test as if you're in production. That's where this testing is going to pay off in the end. Next is execution, deploying the changes. The key here is to document everything. Your future self will thank you for thorough documentation. Finally, the post-implementation review verifies success and documents any lessons learned. Every change, successful or not, helps to improve the process. Remember that tools like ServiceNow or Jira can help track this process. Skipping steps invites vulnerabilities. Think about it. How would you handle an emergency security patch during peak business hours? Now, there's different development methodologies you should be aware of for both the CISSP exam and real-world practice. The first one is Agile. This is a fast-paced, adaptable approach with short sprints and close teamwork. From a security perspective, Agile embeds security directly into sprint planning through dedicated user stories and incorporates threat modeling through backlog grooming. This method works well for projects requiring quick security posture adaptations. The next one is Waterfall. This is the traditional step-by-step approach. Think of it like an actual waterfall, where one step flows down to the next, and you must complete each step fully before you can move forward. You can't exactly go up the waterfall. You establish all of your security requirements up front, and each phase requires formal security sign-off before proceeding. This methodology is great for highly regulated environments like healthcare or finance, where documentation and compliance are critical. Keep in mind, though, that once you start, you can't go back and make any changes. So once those security requirements are approved and you move forward, they're set in stone. There's less flexibility here for adjustments. The spiral model focuses intensively on risk. It analyzes risk at each iteration, creating valuable security testing feedback loops. This makes Spiral ideal for high-risk systems, where thorough validation is essential. Now, DevOps unifies development and operations. Its key security features include automated security scanning in the CI/CD pipeline and continuous vulnerability assessments. The main challenge is maintaining security at the same rapid pace as your deployments. And then finally, DevSecOps elevates DevOps by making security a first-class citizen. It embeds security champions within development teams and implements automated security gates throughout testing. This approach is great for modern applications that need security integrated into every development step. Now, within DevSecOps, we have our operations team, who are the experts managing your infrastructure and handling all of those deployments. They're the bridge between development and production. Then there's our QA team, our quality gatekeepers who rigorously test everything to make sure it meets our standards. Without them, we'd be flying totally blind. Finally, we have our security team. They implement controls and conduct reviews throughout the entire process, making sure that security isn't just an afterthought, but that it's built into everything that we do. This integrated product team or IPT approach eliminates those traditional silos, enabling faster development cycles, earlier detection of security issues, and improved communication between teams. In DevSecOps, security becomes an integral part of the process, from initial planning through deployment, with automated security checks throughout the entire pipeline. For example, when developing a new feature, security teams review designs early. Developers implement security controls during coding, and automated scans verify security before deployment. Now, different projects require different approaches. Modern development many times will combine these various methodologies to leverage their unique strengths. To make these combinations successful, you should follow these important best practices. First, clearly define your transition points so teams know exactly when to switch between methodologies. Second, maintain consistent security controls across all of your approaches. Security cannot be compromised when you're switching methods up. Finally, and you guessed it, document everything thoroughly. Teams must always know which methodology applies to each project phase. Remember that while methodology flexibility is valuable, security requirements must remain front and center regardless of the combinations that you use. Now, Canary testing is an important development strategy we should discuss. It was named after miners who use canaries to detect dangerous gases. In software deployment, you release new code to a small subset of your users to detect potential issues before pushing a full rollout. Companies like Google and Amazon use this approach extensively. So here's how a canary testing works. We begin with a canary group. This is a tiny subset of users, usually about 1 to 5% of your total user base. These users serve as your early warning system. For example, Facebook caught a critical authentication bug during a canary deployment in 2021, preventing what could have been a major security incident. While these users interact with the new version, we monitor 3 key metrics: performance, how fast is everything loading? Error rates, are we seeing any unexpected issues? And user feedback, what are people actually experiencing? If everything looks good with our canary group, we gradually expand deployment, first to 20% of our users, then 50%, and finally to everyone. This measured approach is important for maintaining system stability. From a security perspective, canary testing helps us catch 3 major types of issues: vulnerabilities that only appear in production environments, unexpected authentication issues before they affect all users, and authorization problems where users might have incorrect access levels. Now, maturity models provide frameworks to assess and improve an organization's security practices. There's 2 important models here: the Capability Maturity Model Integration, or CMMI, and OWASP Software Assurance Maturity Model, or SAMM. CMMI works like a ladder with 6 distinct maturity levels. Each level represents a step forward in your organization's security maturity. At level 0, you're dealing with incomplete processes. Think of this as flying blind. You can't predict what's going to happen because there's no structure in place. Moving up to level 1, you've started implementing basic reactive processes. You're addressing problems as they come up, which is better than nothing, but you're still just putting out fires. At level 2, things get a little bit more organized. You've got plans in place and you're actually measuring what you're doing. This is where you start to see real improvement. Level 3 is where it gets exciting. You've implemented organization-wide standardized processes. Everyone's following the same playbook, which creates consistency across your entire operation. When you reach level 4, you're making decisions based on data. You're using detailed metrics to guide your choices, which means you're working smarter, not harder. Finally, at level 5, you've achieved what we call a continuous improvement culture. You're not just maintaining, you're constantly optimizing and getting better. This is where true security excellence lives. For example, a financial services company progressed from CMMI Level 1's basic testing to Level 4's automated security scans and metrics, reducing security incidents by 60%. Their next goal is Level 5, where they'll use predictive analytics for continuous security optimization. Now, OWASP SAMM has 3 maturity levels. At the initial level, you've got your basic security practices in place. They work, but they're not always consistent. You might be doing security testing, but it's ad hoc rather than systematic. Moving up to the structured level, you've established defined processes across 3 key areas: governance, design, and implementation. This means your security practices are now standardized and repeatable. Every team follows the same security playbook. At the highest level, optimized, you're not just following processes, you're actively improving them. You're using data to drive your security decisions, and you've automated many of your security processes. This is where you want to be, where security is not just a checkbox, but a continuous cycle of improvement. So, what is this software development ecosystem? A software development ecosystem is an integrated digital environment where components work together to create and maintain software. It consists of 3 components working together in harmony. First are the development tools, like building blocks that include our code, programming languages, and IDEs that streamline development. Second are the processes, the conveyor belts of our digital factory. These encompass build pipelines that move code through stages, testing frameworks that ensure quality, and security tools that maintain protection. Third, and most importantly, are the people, the heart and soul of any ecosystem. This includes development teams writing code, security experts maintaining vigilance, and operations staff keeping everything running smoothly. Just as in nature, if any component becomes compromised, whether it's an outdated tool or weak security control, the entire system becomes vulnerable. This is why maintaining ecosystem health through regular updates, security checks, and proper access controls is crucial. A development ecosystem integrates tools and processes to support secure software development. There's 3 critical components that form its foundation. The CI/CD, or continuous integration and deployment, serves as your automated security guard. When developers commit code, it flows through security checkpoints, scanning for vulnerabilities, running compliance checks, and ensuring security before deployment. It's like having a vigilant security team working 24/7. SOAR, or Security Orchestration, Automation, and Response, acts as your automated incident response system. Like a tireless security expert, SOAR continuously monitors your development process, detecting and responding to potential threats throughout the entire development lifecycle. Then SCM, or Source Code Management, functions as your code vault keeper. It provides a secure vault for your code with access controls, digital signatures, and detailed audit logs. Every change is tracked and logged, making sure there's complete accountability for code modifications. Now let's look at these critical components of a secure development ecosystem and why each of them matters for your security posture. First, programming languages. Security should be your top priority in your selection. Rust, for example, features a unique ownership model that prevents memory-related vulnerabilities. Python offers extensive security libraries with robust sandboxing capabilities. The Heartbleed vulnerability caused by buffer overflows in C and C++ demonstrates why language choice is crucial. Libraries are equally important. Use trusted sources and implement automated dependency scanning as your first line of defense. For development tools, standardization is essential. Use approved compilers with security flags enabled, and configure debuggers to prevent information leakage. Maintain a vetted tools registry to prevent future complications. IDE security requires specific attention. Configure code analysis and linting, and enable security inspections. Be cautious of malicious extensions that could access your source code. Runtime environments demand careful configuration. Set up the Java VM Security Manager properly, and for Node.js, enable the secure heap flag. The Log4 shell vulnerability, which exploited Java runtime weaknesses, illustrates the importance of proper runtime security. Your CI/CD pipeline requires automated security checks. Configure SAST and dependency scanning and implement security plugins. Stay vigilant. Supply chain attacks often target CI/CD systems. For source control, enable signed commits. and maintain detailed change logs. Unauthorized code changes can introduce backdoors, making these precautions essential. Finally, secure your code repositories, require MFA and branch protection, and mandate code reviews before merging. The SolarWinds breach, which began with a compromised build system, demonstrates the importance of repository security. So let's quickly explore the evolution of programming languages and their security features. This is a fascinating journey that shows us how security has evolved over time. First-generation languages consisted of pure binary code, with direct hardware instructions. While efficient, these languages had significant security drawbacks. They carried a high risk of memory errors and lacked any built-in security features. Second-generation languages like assembly brought improvements through symbolic machine code, making programs more readable. Though they introduced basic error detection, they remained vulnerable to memory issues. Third-generation languages like C and Fortran ushered in the modern era with human-readable syntax, introducing structured programming concepts and basic memory protection, making a significant security advancement. Fourth-generation languages like Java, Python, and C# represent a massive leap in security. These languages feature built-in security controls, automatic memory management to prevent memory leaks, and strong type checking to catch errors before they become vulnerabilities. Finally, fifth-generation languages like Prolog and Mercury take an innovative approach through logic-based programming, built-in constraint checking, and reduced implementation risks. Though less widely adopted, they hint at future directions in language security. So let's talk about those translators. These are the tools that convert our human-readable code into machine-executable instructions. There's two main types to understand. First are the compilers. These act as translators that read your entire program at once, similar to reading a whole book before translating it. Compilers offer powerful capabilities. They optimize your code and add crucial security features like stack protection to prevent buffer overflows, and bounds checking to prevent unauthorized memory access. The second type, interpreters, are used with languages like Python and Node.js. They work differently. They translate your code line by line, like a translator reading each sentence as you go. Interpreters excel at providing real-time security features. They can sandbox your code to keep it isolated and safe, while handling memory management automatically to prevent memory leaks. When working with translators, there's several critical security practices that you should know about. First, always use verified translators from trusted sources. This is crucial because malicious translators can insert backdoors into your code. If you can't trust your translator, you can't trust the code it produces. Second, keep your translators updated with the latest security patches to address vulnerabilities. Third, enable all relevant security flags and checks. These are your first line of defense against common security issues. Finally, always verify your compiler and interpreter signatures to make sure they haven't been tampered with. For a simple example, when we write print hello, our trusted translator converts it into machine code. This process must be secure at every step to make sure your code becomes secure CPU instructions. Now, runtime security is critical when your code runs in production. We need multiple layers of protection to keep it secure. Let's look at our essential security controls. Think of firewalls and access controls as security guards. They protect your application's perimeter. Memory protection acts like safety rails, preventing buffer overflows that attackers love to exploit. Input validation serves as your bouncer, carefully checking everything entering your application to prevent injection attacks. And session management, that's your ID check system, making sure users are who they claim to be throughout their entire visit. So what vulnerabilities should you watch out for? Memory leaks are like slow water drips. They seem minor, but eventually flood your performance. Race conditions are tricky. Imagine two people trying to go through a door simultaneously. In code, this can cause serious security issues. Watch out for unauthorized access attempts. They're like someone testing your locks, looking for a way in. And resource exhaustion attacks? Think of these as someone deliberately trying to overwhelm your system resources. For monitoring, you must keep a constant eye on your running applications. There's 4 key monitoring components you need. The first is real-time logging and alerts, your security radar system that constantly watches for suspicious activity and notifies you immediately. Next is performance metric tracking, like a health monitor for your application, telling you if your system is running smoothly or showing signs of stress that could indicate a security issue. Third is security event correlation. Think of it as being a security detective, connecting the dots between seemingly unrelated events that might be part of a larger security threat. Finally, there's automated intrusion detection, your tireless security guard that continuously scans for unauthorized access or suspicious behavior. Remember that proper configuration and robust error handling are your first line of defense. Attackers frequently target running applications. Now, secure programming requires implementing robust defensive measures throughout your code. Input validation is essential. Use strict type checking, length limits, and character filtering to prevent injection attacks and buffer overflows. Implement comprehensive error handling with try-catch blocks, appropriate logging, and fallback mechanisms. Object-oriented security principles are important concepts that every security-minded developer must understand. So let's break them down. The first one is inheritance, which works like a security family tree. You start with a base security class, say an abstract authenticator, then extend it to create specialized versions. For example, you might create an OAuth 2 authenticator that inherits all core security features while adding specific OAuth 2 functionality. This ensures consistent security across your authentication system. Next is encapsulation, which acts as a secure vault in your code. It keeps sensitive data like encryption keys and access tokens locked away from direct outside access. Only authorized methods can interact with this protected data, which is important for maintaining confidentiality. Finally, there's polymorphism, where things get fascinating. It lets you adapt security controls based on context. It might have different validation rules for different input types. One set for email addresses, another for passwords, and another for API tokens. Your code can handle all these cases elegantly while maintaining strict security standards. Follow the OWASP Top 10 guidelines to prevent common vulnerabilities like cross-site scripting, SQL injection, and broken authentication. Implement input sanitization, output encoding, and proper session management according to OWASP secure coding practices. Secure programming goes beyond just using tools. It requires a security-focused mindset. Inheritance enables the sharing of proven security patterns. Encapsulation safeguards sensitive data. And polymorphism allows security controls to adapt to different contexts. To maintain strong security, always validate inputs rigorously, optimize resource usage, and conceal implementation details like stack traces, and use OWASP guidelines as your security compass. Remember that security must be integrated into every line of code. Now, code obfuscation deliberately makes source code harder to understand while maintaining its functionality. It uses several techniques. Lexical obfuscation renames variables and functions. Data obfuscation changes how data is stored. And control flow obfuscation modifies execution paths. Though effective as a security measure, always preserve the original source code. Debugging obfuscated code can be extremely difficult when any issues occur. Now let's explore the different environments and their security controls. This is important information. So first is the development environment, where code comes to life. Here we must implement strong secure coding practices from the very start, including restricted access controls to protect our source code, and regular security scans that serve as health checkups for our code base. Next is the testing environment, our safety net before production. It must remain completely isolated from the production environment to prevent cross-contamination. We use only sanitized test data here, never production data, and perform thorough security testing. We also run constant anomaly detection to catch unusual behavior before it reaches production. Finally, there's the production environment, where the rubber meets the road. This environment demands our most robust security measures, hardened configurations with zero room for vulnerabilities, strict access management, and I mean strict, plus comprehensive logging and continuous monitoring. Since this is where our actual users are, we can't afford any mistakes here. Remember that a breach in any environment can compromise the entire system, so maintain strong boundaries through network segmentation, access controls, and constant vigilance. Now, your database management systems, or DBMS, they need multiple security layers all working together, from hardware and software to SQL, user controls, and data protection. Concurrency management uses lock mechanisms to handle multiple users accessing the system simultaneously. The asset properties, including atomicity, consistency, isolation, and durability, safeguard transaction reliability and prevent data corruption. These fundamental principles make sure your database remains both secure and consistent. A comprehensive DBMS security approach requires multiple layers of protection. Hardened servers and regular patches protect against infrastructure vulnerabilities, while robust SQL injection blocks and input validation safeguard your applications. User training and access controls defend against insider threats, with encryption providing an additional critical defense layer. For relational databases, properly secured primary and foreign key relationships are essential, while concurrency controls through locks and ACID properties maintain data integrity when multiple users access the system. Now, metadata demands careful handling in secure development. Document properties, exit data, and system logs may inadvertently expose sensitive details about your organization. To protect against this, always sanitize files before sharing. Implement strict access controls, and encrypt sensitive metadata. Should you discover a metadata leak, report it immediately through proper incident response channels. Testing serves as your security safety net by catching vulnerabilities early. SAST, or Static Application Security Testing, examines source code directly. DAST, or Dynamic Application Security Testing, tests live applications. IAST, or Interactive Application Security Testing, provides real-time monitoring. And fuzzing exposes weaknesses by injecting unexpected data. For maximum protection, integrate SAST into your CI/CD pipeline and conduct fuzz testing during QA. Both are essential for robust security. Now let's review the key points from today. First, we covered security integration. Remember, this isn't a mere checkbox. Security must be woven throughout every phase of your SDLC. There's no room for shortcuts here. Next, we explored security frameworks, particularly things like DevSecOps and OWASP SAMM. These aren't just buzzwords. They're proven structures that provide a solid foundation for our security practices. I love these frameworks because they offer clear, actionable guidelines for implementing security. We also covered environment protection, which is vital. Think about your entire development ecosystem, from code to tools to deployment pipeline. All of this needs robust security controls. Finally, we discussed continuous testing, covering 3 key approaches: SAST, DAST, and fuzzing. Together, these form your complete testing strategy across the development lifecycle. Now keep practicing these concepts. You're all making excellent progress in understanding software security fundamentals. All right, that's it for Objectives 8.1 and 8.2. You're crushing the CISSP journey. Keep that momentum going. If you need to revisit anything, no worries. These recordings stay on YouTube, and I'll add chapters after the stream so you can jump to specific topics. Mastering this stuff is a huge step towards your CISSP goal, and these concepts will keep popping up. So tie them to real-world scenarios. Stay curious and keep practicing. You're doing awesome. Now, who's ready for the after party? I'm heading to our Study GRC Discord server's CISSP voice channel right now. It's the perfect place for questions, insights, and connecting with the community. If you're not in the Discord yet, you can visit cissp.brewlight.io for the Discord link. And don't forget to grab your CISSP role when you join to gain full access to our study channels. Our next session will be Tuesday, June 10th at 6 p.m. U.S. Central Time. We'll wrap up Domain 8, Software Development Security. Thanks for watching, and I'll see you in Discord.